In this worked example, for vectors, I'm given three vectors, and I want to find the fourth such that the sum of all the vectors is equal to 0. Even if I'm given the picture with the vectors, I'm going to draw that picture again, because that's an important part of the visualization process. I'm going to have lots of blank scratch paper, and I'm going to make my pictures and graphs very large. When you're dealing with lots of trigonometry, it's important to have big pictures so that you can see everything that's going on. So I have three vectors, and the first vector is coming off here with an angle of 30 degrees counterclockwise from the positive x-axis, and I'm told that it has a magnitude of 80 units. We'll say it's meters, but I'm not going to keep writing meters all the time. So it's of 80 units. So there's another vector that's counterclockwise from the positive y-axis of 30 degrees, and it has a magnitude of 100 units, say meters. And then there's a third vector that's counterclockwise from the negative x-axis at 53 degrees, and it has a magnitude of 50 meters. Okay, so the first thing I'm going to do is I'm going to look a little bit at this and see what this is telling me. Interestingly, I note that B and A are perpendicular to each other. I'm going to write that down. I don't know if that's useful information, but that's something just by taking a moment to look at the system to try to extract what I know about it. The other thing I notice is that I've got a couple 30, 60, 90 triangles. That's useful information. Let me get a different color here. And so here's a 30, 60, 90, 30, 60, 90 triangles. 30, 60, 90 triangles are useful because I immediately know what the trig functions are. Those are easily sine of 30 is 1/2, cosine of 30, square root of 3 over 2 are directly known. I don't have to worry about trying to calculate them. And then the reverse for 60 degrees. Of course, sine of 60 is square root of 3 over 2, and cosine of 60 is 1/2. Okay, I also know that I have a 3, 4, 5 triangle. So here's the first thing I've noticed, the second thing, and here's the third thing I've noticed is I have a 3, 4, 5 triangle. Well, what do I mean by that? And this is sort of a triangle I think everyone probably should have seen, is that if you have one length of a triangle, of a right triangle is 3, another length is 4, then the hypotenuse is 5. And the angles, the relative angles of that triangle, one of them is 53 degrees to two significant figures, and the other one is then 37 degrees. So by noting that this angle, the C relative to the negative x-axis, is 53 degrees, I note that I have a 3, 4, 5 triangle. And that is useful because, again, the sine of cosine of the angles are easy. So sine of 53 is 4/5, and cosine of 53 degrees is 3/5, 0.8 or 0.6. So you notice that I've extracted some interesting and meaningful information out of this problem by not just plowing ahead looking for a solution, but getting a good picture of it and looking at it, trying to understand it, and brainstorming a little bit. Okay, so I have some information, and so now I want to go ahead and try to solve. And so I want a fourth vector such that the sum of all the vectors is equal to 0. So if I sum all the vectors, I have A plus B plus C plus something else. Well, I can call that whatever I want. I'm going to be really creative. Call that D. and the sum of all those vectors is equal to 0. Okay, so if I solve for my unknown vector, that might be equal to the negative sum of a plus b plus c. And so I guess I can add a, b, and c together and come up with and then take the opposite of it. That would be a way to solve. I'm still sort of brainstorming, figuring out a way to solve. I can think about breaking it into components, or I can think about doing it graphically. My intuition tells me to look at this graphically. I mean, sorry, to do it components, because it seems to me graphically might get difficult. And so that's the direction I would go. However, just as an example, let's take a look at it graphically and see what it might look like. I want to keep the graph there. So if I were to say, try to look at this graphically, what would that entail? So I'm going to keep my axes like this. So here's plus x. I'm going to do another graph here, plus y. So what would this look like? So A, it comes off here with a length of 80, say, and this is 30 degrees. And if I'm going to add then tail to head method, then B is, I'm going to translate B to the tail of B to the tip of A. So it's going to come off here. So this is 80, length of 80, and then B was a length of 100, and it's perpendicular to A. So it comes off in this direction, as shown. And then C, I'll have to be able to get C graphically. Let me draw a new sort of set of perpendicular axes here at the tip of B. And so now C is going to come off at 50. So in this direction, a length of 50 at an angle of about 53. So I'm just sketching. I don't know exactly what this looks like, but it's going to be something along those lines. And now for the sum of these vectors to be equal to 0, I'm looking for the vector that goes from the tip of C back to the origin. That now is the vector D. And so presumably I can use trigonometry to come up with the direction and the magnitude of D by breaking up this all of this into all the different triangles. And looking at that, I think my initial impression was correct in that would really be some tedious trigonometry. I think it's better to break it up into components. However, we have learned some useful information by doing it this way. It's pretty clear just by doing a sketch that the resulting vector D is going to be essentially straight down, mostly in the negative y-axis, just by doing a sketch. So that's useful information. Even if I don't decide to solve the problem this way, I have some information that when I do come up with a solution, I can check to see whether it turns up to the way I understand. And this is how I go about solving problems. You always come up with different ways to look at a problem to see that when you finally come up with an answer, it is consistent with how you understand the problem. Okay, so let's go back to solving it via components. All right, so what I'm going to do is then I'm going to look at this relationship here. And by doing that, I'm going to try to come up with each vector in component form, and then I'm going to add them all to set them equal to 0. And so I could in fact try to add A, B, and C and take the inverse, but I'm going to look at it in a different way, and I'll show you how that is. So first, I'm going to get all the vectors in component form. So I need the x component of A. And so that is going to be, the x component is going to be the length of this side of this triangle. And that length, I use trigonometry. And so that's the hypotenuse, 100, times cosine of 30, sorry, A is length 80. A is length 80 times the cosine of 30 degrees, which is the square root of 3 over 2, and it is in the positive x direction. All right, so that's the component x. So in the y, I have now, I'll get a different color. So here's the y component is going to be the length of that triangle, and so the length of that triangle is the hypotenuse times sine of the angle, which is 1/2, and it's also in the positive y direction. Okay, so now b, the vector b. The x component now is the length of this side of this triangle, the length that's parallel to the x-axis. So it's the length of this triangle. So in this case, the length is the hypotenuse times the sine of the angle. Hypotenuse of b is 100, and sine of the angle is 1/2. And this length is in the negative x direction. So this is a negative I hat. So let me pause for a moment to emphasize what I did here. The first of all is I didn't use any formulas that you might have seen, like the x component is r cos theta. The y component is r sine theta that you might have seen in a book. No, I always go to the picture and I draw a triangle and I find the proper x component as a length of that triangle. For A, it happened to be, the x component happened to be the hypotenuse times the cosine of the angle that I had, while for the second triangle, the x component happened to be the hypotenuse times the sine of the angle. I always go to the specific triangle in my diagram to be able to apply the trigonometry. And also, I don't rely on formulas to come up with my signs. I always go to my figure, and here, the figure told me for A, vector A, both components were positive, and my figure told me that for B, the x component was in the negative x direction. And then, of course, the y component is going to be in the positive y direction. Okay, to calculate that y component is then using trigonometry, the hypotenuse times the cosine of the angle, which is the square root of 3 over 2 j hat. Right, and now C, my final vector, is equal to, now I want the x component, which is the length of this triangle, which is 30, and it's in the negative x direction from my figure. And then the y component is 40, and is also in the negative. Now you see how I was just able to write that down, because this, the x component, is going to be the hypotenuse times cosine of 53 degrees. I already noticed that cosine is 3/5. Where did I get 3/3? 3/5, of course. And so 3/5 times 50 is 30, and then the y component was the hypotenuse times the sine of the angle, which is the hypotenuse times 4/5. 50 times 4 is 40. And also, it's just a similar triangle. 3, 4, 5 triangle turns into a 30, 40, 50 triangle. And so my initial observation about the problem, trying to understand it, greatly simplifies my calculation later on. Okay, so again, now my D is my unknown, and so it has an x component and a y component. And if I sum all of these vectors, I get 0. And so for the resulting sum of the vectors to be 0, it must have a 0 x component plus a 0 y component. Now you can see why this is convenient, because what I had was a vector relationship. The sum of all the vectors had to be 0. But I've been able to turn that into two scalar equations. The sums of all the x components must be 0, and the sum of all the y components must be 0. So if I look at the sort of the x components, I have the following relationship. I have 40 times the square root of 3, that 80 over 2 there, minus 80, that's minus 50 here, minus 30, plus the x component of my final vector must be equal to 0. And so if I just solve, that x component then is 80 minus 40 times the square root of 3, and now I finally have something that I can plug into my calculator. See, I don't plug things into my calculator until it's in as reduced form as possible to save calculator error possibilities. And so the result is 10.7. Again, whatever units I started out with, we can say it's meters. All right, and so now for this is sort of the x component. So in the y components, I have, well, here's a positive 40. Here's a negative 40, so that adds to 0. So I end up with 50 times the square root of 3 plus the y component of my vector is equal to 0. Well, so my y component then is negative 86.6. So now I have my final vector in component form. My final vector is 10.7 I hat minus 86.6 j hat. Does this make sense? Well, note that just like I had anticipated, this vector points primarily in the negative j hat direction. It turns out to have a positive x component, and I didn't exactly get that from my original diagram, but again, that was a sketch. Qualitatively, it had a much smaller x component compared to the y component. That is consistent with what I had imagined it would be. So okay, so that's an important check on what I wanted to do. All right. So now we want to find what sort of magnitude it is and how it is oriented from the positive x-axis. So the magnitude is then the square root of the sums of the squares of the components. So 10.7 square root of 10.7 squared plus 86.6 squared, and that I just plug into my calculator, which gives me 87.3, say, meters. And now I want to know how it is oriented counterclockwise. We'll say counterclockwise from the positive x-axis. So how do I find that? Again, I never use some sort of baked-in formula for that. Always go to the picture and the diagram. Okay, and so here here's some angle that I can find from a triangle, because I know its components. Let's get a better picture here. So lots of blank scratch paper and nice big pictures. So we have this vector that comes like this, and it has some and it makes a right triangle, where this side of the triangle we know has a length of 10.7, and this side of the triangle has a length of 86.6, and so that allows us to find this angle theta, because of tangent of theta is equal to 10.7 over 86.6. And I can plug that into my calculator to find the angle. I want to tell you a very short story, is that when I did this, when I was working this out, the first number I got out of my calculator was 58.3 degrees. And so what I've seen a lot of students do is simply write that number down because that is what their calculator told them. But that doesn't make any sense. I mean, we just noticed. I mean, that was part of our study of this problem is that this vector has a large y component compared to the x component. And so from this picture, how on earth could this angle right here be greater than 45 degrees? And the answer was it can't. That was just a calculator error. So I said, oh, I must have plugged in numbers wrong, and it did. When I did it again, I got an angle of 7.04 degrees, and which makes perfect sense. I expected that angle to be small. And so my problem asked for counterclockwise from the positive x-axis. Here's the positive x-axis. And counterclockwise is going to be this way. So the final angle that I'm interested in is going to be the 270 degrees plus the final 7.04, and so to three significant figures, this is going to be 277 degree angle counterclockwise. So my final answer in descriptive form is going to be a magnitude of 87.3 in whatever units I'm interested in, 277 degrees counterclockwise from positive x-axis. All right, and so notice that a couple important points is when I found the angle just from the most basic triangle using my basic trigonometry rules. Then I related it back to whatever the problem wanted by going back to my picture and looking where is my vector relative to my picture so I can see how it is oriented from the positive x-axis. Always use your pictures to do that sort of calculation. Always go back to your picture to make sure it makes sense, to go back to what the problem is asking for. And also, always double check to make sure your numbers are reasonable. I got a number that was clearly wrong, and that gave me an idea that my calculation was an error. Never trust the numbers that come out of your calculator. Always check them first to see that they make sense.